All right, let's dive right into this explainer. Over the last year or so, generative AI has just completely taken over the conversation. And let's be real, it kind of feels like magic, right? You type a quick prompt and boom, you suddenly have a fully written essay, a gorgeous piece of art, or even complex code. But driving this entire boom, the actual engine behind all of this magic, are AI chips. We're talking about pieces of hardware that are often no bigger than the palm of your hand. Yet they are single-handedly driving a massive technological revolution that is completely reshaping how we process information on a global scale.
And the financial scale of this hardware revolution is honestly just as staggering as the tech itself. Just consider the numbers for a second. Originally, analysts thought the total market for data center AI accelerators was going to be substantial, around $150 billion. But because demand has skyrocketed at a pace literally no one saw coming, that expectation has completely shifted. The market is now projected to exceed an incredible $400 billion. That is a massive jump, and it shows exactly why the world's tech titans are currently locked in an absolute arms race to design better, faster chips.
So here is our roadmap for today. We'll start with the AI chip boom, then peek inside microscopic semiconductors. After that, we'll compare CPUs to AI chips, break down training, inference, and heat, dive into the corporate battle, and finally look beyond the current hype. Let's get started.
Part 1. The AI chip boom and this unprecedented demand. Let's set the stage and look at where these custom engines are actually born, like in Amazon's dedicated chip labs down in Austin, Texas.
Moving on to Part 2. Inside the microscopic semiconductors, from wafer to die. Let's zoom way in to see how these are built from the ground up. Let's break down the physical anatomy of what we casually call a chip. Right out of the manufacturing plant, companies receive what is called a wafer. You can picture the wafer as this raw, circular foundation. From this large wafer, manufacturers slice out individual little rectangles. These rectangles are called dice or a single die. The die is the piece that actually contains the compute elements, the parts doing all the heavy mathematical lifting. So when people talk about an AI chip, they're usually referring to this individual die once it's been all packaged up. And here is where the sheer scale of this engineering gets absolutely mind-boggling. Inside just one of those little rectangular dice, there are tens of billions of microscopic semiconductors called transistors. Tens of billions. These tiny transistors are constantly flipping on and off, communicating inputs and outputs to perform calculations. And when we say microscopic, we really mean it. Roughly speaking, the size of each one of these transistors is about 1/millionth of a centimeter. We are quite literally packing city-sized networks of computational power into a space smaller than you can possibly imagine. Part 3. CPUs versus AI chips and the power of parallel processing. So, if everything uses transistors, what makes an AI chip so fundamentally different from the standard CPUs sitting in your phone right now? Well, it all comes down to sequential versus parallel processing. Think of your standard CPU like a single master chef in a restaurant kitchen. This chef has a few very powerful cores and is incredible at executing highly complex tasks, but they do them sequentially, one step after another. If you ask a CPU to generate a digital image of a cat, it's going to draw that cat just a couple of pixels at a time. It's fast, sure, but it's doing it in order. Now, an AI chip is completely different. Think of an AI chip like an army of thousands of specialized prep cooks crammed into that exact same kitchen. They might not each be a world-class master chef, but there are thousands of them working simultaneously. This is parallel processing. An AI chip has thousands of smaller cores that can process hundreds or thousands of those cat pixels all at the exact same time, generating the whole cat basically at once. That parallel architecture is the real secret sauce of artificial intelligence. Though honestly, with thousands of prep cooks, you just have to hope they clean up the kitchen afterward. Part 4. Training, inference, and heat. The heavy lifting of AI. Let's look at the two distinct functions these highly specialized chips are engineered to handle. Let's walk through these two crucial steps. Step 1 is training. This is hands down the hardest part of the process. Training is where you feed an AI model millions of examples, like say millions of pictures of cats, so it can actually learn what a cat looks like. Because of the sheer massive volume of data, training requires a colossal amount of compute power. You don't just use one chip for this, you use tens of thousands of chips working together at the same time. Then comes step 2, which is inference. This is what happens when you type a prompt and ask the chatbot to generate a brand new image of a cat. The AI uses the knowledge it gained during training to infer or generate an entirely original output. Inference is way less computationally heavy, typically running on a cluster of just 1 to 16 chips. But of course, here is the catch. Whether you're training on tens of thousands of chips or just running inference on a handful, processing this massive amount of AI data continuously requires immense, staggering amounts of energy. And in physics, massive energy consumption means you generate extreme, downright dangerous levels of heat. If left unmanaged, these chips would get so hot they would literally destroy themselves. So, how do engineers solve this meltdown problem? The hardware integration process is fascinating. To manage those high operating temperatures, the chips are physically attached to large metal heat sinks. These are heavy pieces of metal specifically designed with air vents to rapidly pull and dissipate the heat away from those microscopic transistors. Before they even see a data center, engineers subject these chips to extreme temperatures just to test their reliability. Once they pass, the chips are mounted onto baseboards, usually 8 cards to a board. Then they're interconnected within servers using incredibly high bandwidth and low latency networks. This setup allows all the different devices inside the server to work collectively on the same massive computation. So when you ask a chatbot a question, it hits a CPU, passes the data to a networked army of these AI chips to do the gigantic parallel calculation, and then zips the result right back to you. Part 5. The Corporate Chip Battle, Designing for Dominance. Let's zoom out from the server racks for a minute and step into the high-stakes boardrooms.
It's really interesting to see the divide between the major players right now. The market is currently dominated by Nvidia. Their strategy is to be the premier general chip provider to all different types of customers running all sorts of different workloads. Without a doubt, they are the king of the hill today. But on the other side of the ring, you have the major cloud providers, giants like Microsoft, Amazon, and Google. Their strategy? Build their own custom chips. Now, why would they do that? 2 massive reasons. First is performance. They want to tightly optimize the hardware specifically for their own proprietary cloud software to gain a performance edge. And second, economics. By building their own custom chips in-house, they simply don't have to pay the wildly juicy profit margins that Nvidia demands on the sale of every single unit. It's a classic high-stakes battle of the incumbent general supplier versus vertical integration.
Finally, Part 6. Beyond the AI hype, looking to the future. With all this investment, is generative AI just a passing consumer fad? There's a brilliant insight from the experts we reviewed that tackles this perfectly. They noted that, while there might be something like a dot-com bubble for the current AI hype cycle, at the end of the dot-com bubble was still the internet. That is such a powerful perspective. It reminds us that regardless of whether consumer excitement has peaks and valleys, or whether specific AI startups boom or bust, the foundational physical infrastructure, those billions of microscopic transistors performing parallel processing, is very real, and it is absolutely here to stay. Because of that reality, companies are buckling in for the long haul. Cloud providers like Amazon and Microsoft are currently offering their customers a mixture, giving them the choice between using in-house custom hardware or sticking with Nvidia's chips. But the most crucial takeaway here is the relentless, exhausting pace of innovation. Tech leaders note that they are seeing a massive step up in capabilities, which demands significant generation-to-generation hardware improvements. The AI software is advancing so incredibly fast that the physical chips have to constantly evolve just to keep up. The AI chips rolling out next year are going to make the ones we just talked about look like ancient history.
And that brings us to the ultimate question. We've seen how these microscopic parallel processors function, how engineers manage their extreme heat, and how they train massive AI models. But as this generation-to-generation hardware innovation aggressively accelerates, who is actually going to win the battle for the world's AI computing workloads? Will Nvidia maintain its iron grip on the market, or will the cloud giants succeed in rewriting the rules with their custom silicon? It's an incredible technological arms race, and it's all happening on pieces of silicon the size of your palm. Thank you so much for joining me today to unpack this explainer. See you next time.